All right, in this last section, we're going to take a look at some AP style free response problems related to titrations. Here's free response problem 1. Aniline, a weak base, reacts with water according to the reaction shown. So we have aniline, this is the weak base, in water to form its conjugate acid and the hydroxide ion. Write the equilibrium expression Kb for the reaction represented above. A sample of aniline is dissolved in water to produce 25 milliliters of 0.1 molar solution. The pH of the solution is 8.82. Calculate the equilibrium constant Kb for the reaction. And then C, the solution in part B is titrated with 0.1 molar HCl. Calculate the pH of the solution when 5 milliliters of the acid has been added. Part D, which has 2 parts. 1, calculate the pH at the equivalence point of the titration of part C. And then 2, provide the hydrolysis step of the conjugate acid in this zone to justify your answer. Finally, E, the pKa values for several indicators are given below. Which indicator is most suitable for the titration? And justify your answer. So we have 3 different indicators, 3 different pKa values that we'll choose from. All right, so part A, pretty straightforward, writing the equilibrium expression Kb for the reaction. So we've already been given the reaction in the problem. We just need to have the concentration of the products multiplied on the top, and then divide by the concentration of the base on the bottom. And that's our Kb expression. All right, in part B, a sample of aniline is dissolved in water to produce 25 milliliters, that's our volume, of a 0.1 molar solution. That's our concentration of aniline. We measure the pH of that solution, and it's 8.82. Calculate the equilibrium constant, Kb, for this reaction. So first, I need to know the hydroxide ion concentration so that I can use it in that Kb expression that we wrote in part A. So that's the first thing I do. I find the pOH by subtracting the pH from 14. I get 5.18. And then to find the hydroxide concentration, I just do 10 to the minus pOH, or 10 to the minus 5.18, to get a hydroxide ion concentration of 6.61 times 10 to the minus 6. Now, why is that important? Well, the hydroxide ion concentration and the conjugate acid of the aniline base are the same, and so I can substitute that into my Kb expression for the concentration of the acid, the concentration of hydroxide, over the initial concentration of the base, which was given as 0.100, and then calculate the Kb. And if you don't remember kind of how this works, remember we can talk about initially we have all aniline, right? C6H5 NH2, and it's 0.1 molar. And we have no hydroxide, and we have no C6H5NH3 plus, that conjugate acid. And that there's some change, which we'll call X, where this dissociates in water, and we've seen that dissociation. Just go back one slide to part A, and the equation is there. And so we're left with 0.100 minus X, X, and X. So you can see these two concentrations are the same. We call them X, or in this case we calculated it, 6.61 times 10 to the minus 6. And then divide by 0.1, because remember this change is really small. It's negligible compared to the original concentration, so we can ignore it when calculating our Kb. So we get 4.37 times 10 to the minus 10 as our Kb value. All right, here's where things get fun. So the solution in part B, that initial concentration of 0.1 molar aniline, is titrated with 0.1 molar hydrochloric acid, strong acid. Calculate the pH of the solution when 5 milliliters of the acid has been added. So, before anything happens, I have this chart before neutralization, when neutralization occurs, and after neutralization. So before neutralization, how many moles of the aniline do I have? Well, I have my concentration, 0.1 molar, times my volume. And this was given in part B. So it was 0.1 molar aniline in a 25 milliliter solution, right? So we can find the number of moles. We get 0.00250 moles of aniline before any reaction happens. So that's what I've put here. And how much acid or how many moles of acid am I adding? I'm adding 5 milliliters of 0.1 molar HCl. So 0.1 molar times 5 milliliters, or 0.005 liters, is 0.0005 moles of HCl, which you can see represented here. And before any neutralization happens, we don't have any product. We don't have any of that conjugate acid product. Now, all of the hydrogen ion is neutralized. So all of the strong acid is neutralized. We're left with none of it. After some of the aniline is consumed during the neutralization, we're left with 0.002 moles of aniline, and now we've produced some of that conjugate acid product, 0.0005 moles. Now, in the next step, we need to find the concentration. This is essentially now a buffered solution of base and conjugate acid. We need to find the concentration now that we know the moles, and then find the pH. So to do that, we need the total volume of the solution. The total volume of the solution is 30 milliliters. 25 milliliters of aniline, and 5 milliliters of HCl. So the final molarity is the number of moles of aniline, 0.002 over 0.03, 0.0667 molar. And for the HCl, we just take the moles, 0.0005 over the 30 milliliters, 0.03 liters, and get 0.0167. Now let's use that to calculate the pH. Okay. So we have some base, some acid, and we have this hydrolysis that will occur. We've seen this before in water to produce. So here's our acid-base equilibrium. Right? And so we have to reestablish our equilibrium. So here's our initial concentrations of acid, well, base and acid. We'll consume some of the base and produce some of the acid and some of the hydroxide to get these final equilibrium concentrations. Now, remember, assume that X is very, very, very small, right? Much, 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 much less than the concentration of the aniline base. All right. And so what we can do here is assume that the change is small relative to the change X, and use our KB expression to determine X. So we already wrote our KB expression in part A. We're just going to use it now and find X, which is equal to our hydroxide concentration. So KB, which we calculated in part B, and then multiplied by the ratio of these concentrations, 0.0667 coming from here and 0.0167 coming from here. Well, actually coming from here, assuming a small change to get to equilibrium. And then we get a hydroxide ion concentration of 1.75 times 10 to the minus 9 molar. From there, we can calculate the pH. So the pH, or the POH in this case, is the negative log of the hydroxide ion concentration 1.7 times 10 to the minus 9. We get a pOH of 8.76, and that leaves us with a pH of 5.24. There is an alternate method to find the pH using the Henderson-Hasselback equation, because this is just a buffered solution of the aniline base and its conjugate acid. So pOH is equal to pKb plus the log of the acid concentration over the base concentration, which is the minus log of 4.37 times 10 to the minus 10 plus the log of the acid concentration over the base concentration, and just go back one slide to refer to those, gives us a pOH of 8.6 and then a pH, therefore the same as we found in the previous slide, of 5.24. Part D1. So there's two parts here. Let's start with the first one. Calculate the pH at the equivalence point of the titration that we described in part C. So at the equivalence point, the moles of the aniline will equal the moles of H plus added will equal the moles of the conjugate acid formed. So at the equivalence point, moles of acid equal moles of base. And in order to reach the equivalence point, we need 25 milliliters of HCl. And the total volume of the solution is 50 milliliters. So let's just think a little bit about where we got to that. So the equivalence point happens when the moles of acid, which is the concentration times the volume, equals the moles of base. Whoops. All right. So how much acid do we need to add in order to reach our equivalence point? So if we go back to what was given, we know that the concentration of the aniline base is 0.1 molar, and that we start out with 25 milliliters, and we know that the concentration of the HCl being added is also 0.1 molar. So this means the volume of acid that we need to add to get to the equivalence point is 25 milliliters. Okay. Now, if we start with 25 milliliters of base and we add 25 milliliters of acid, the total volume of the solution will be 50 milliliters. So at the equivalence point, there's no more base left, no more aniline left. It has all been neutralized by the HCl. So we have no base and no strong acid left. What we're left with is C6H5NH3+, which undergoes hydrolysis in water. We get C6H5NH2 plus H3O plus. Okay, and we're going to use that to determine our pH. So this is what the pH depends on. Now, the production here is of H3O plus, which comes from the formation of the conjugate base here, and then this is the conjugate acid of water. So we need to work from the Ka instead of the Kb. So I calculated Ka here. Remember, we found Kb back in part B of this. So just substitute that in. We get a Ka of 2.29 times 10 to the minus 5. And then what is this concentration? What concentration do we have? Well, we know the number of moles, right? Which, by the way, how did I get that number of moles? Well, from here, I got it from 25 milliliters. Well, so let's put that in liters, right? If it's a 0.1 molar solution of HCl or aniline in 25 milliliters or 0.205 liters, that gives us 0.00250 moles. So that's where that comes from. And then I divide by the total volume, that 50 milliliters, or 0.05 liters, to get a concentration of the C6H5NH3 plus of 0.05 molar. Based on this number of moles and the total volume, this concentration, 0.05 molar. Now I'm going to write that hydrolysis again, C6H5NH3 in water. So this new equilibrium is established where I'm starting with this concentration of C6H5NH3 plus, and I don't have any products in the beginning. So no aniline and no H3O plus. A change occurs and then equilibrium is reestablished. So I can write the Ka expression, concentration of the aniline times X, where X is H3O plus, over the concentration of C6H5NH3 plus, and then solve for X, given that we now know Ka and we know this initial concentration and the equilibrium concentration if we assume a very small change. We get a hydrogen ion concentration of 1.07 times 10 to the minus 3, which we can use to calculate the pH, 2.97 at the equivalence point. Because of the hydrolysis step, the production of the H3O ions in that previous slide leads to a slightly more acidic solution. Part E, the pKa values for several indicators are given below. Which indicator is most suitable for the titration? So we calculated in part D that the pH at the equivalence point is 2.9 and acidic. We want to pick an indicator with the pKa value closest to the pH at the equivalence point, which would be this first one right here, erythrocene, which has a pKa of 3.